So example 6, we're looking for increasing, decreasing, local max, local mean, concave up, concave down inflection point. So it's something that we've done already. Now there's something that I need to mention. If I give you a function, you need to always pay attention to the domain of the function that I give you. For example, if you have x to the power 2 over 3, this means cube root of x squared. Now the cube root of a function has this domain as a set of real numbers. Why? Because there's a cube root of a negative number. Similarly, this is also cube root. So it means that indirectly, this function has a domain x element of real numbers. Another way for saying real number is just say from minus infinity to infinity. All right. And the reason why I'm mentioning this is because if your domain is a set of real numbers, it means any value you get after equating your first derivative to 0 and where you solve for first derivative is undefined, it's fine because the number will always be part of the set of real numbers. All right. So it's very important to know what your domain is. Okay, so let's see how to do this. So you do you find first derivative. Obviously, it's chain rule, so you need to apply your product rule and do your chain rule. Simplify as much as possible, guys. Sure, we can see here you have to get to this step, and then you need to simplify even further. I got minus 2x minus x is minus 3, so you should be able to get there. All right, and we notice it 3 is still common, so simplify as much as possible. So if I ask you a question increasing and decreasing in my test, I'm going to see that I'm going to check if you can simplify as much as possible. All right, those are some of the things I'm going to check. All right, let's go down. So yeah, your critical values are 0, 4, and 6. Like we said, the domain is a set of real numbers, so we're more than happy to use all of those critical values of 0, 4, and 6. If you actually say, how did they get these critical values? Look at the top. When is the first derivative equals to 0? It's equals to 0 only when the top piece is equals to 0. And that is how they got 4, all right? And then where is the first derivative defined? You see, you must always ask yourself, when is the first derivative undefined? It's undefined when the bottom piece equals to 0. When the bottom piece equals to 0, you have some cube root equals to 0, which x will just be 0. You have cube root of 6 minus x all squared equals to 0. If you solve for that, you just have x equals to 6. That's how they got these values of 0, 4, and 6. All right. Now, as usual, you choose any number you want in between those intervals to get your sign, if it's positive or if it's increasing or decreasing. And you can see that at 0, we have a local minimum. So f of 0 equals to 0 is a local minimum. F of 4 equals to 5 over 3. So this value here at x equals to 4, you get the local maximum. And then at 6, I'm sure you can guess what happened at 6. There's nothing happening there. There's no local mean, there's no local max. Why? Because it's decreasing on both sides. All right. If it's decreasing on both sides of some x value or some critical value, or if it's increasing on both sides, then you don't have a local max or local mean. All right. And then to find concavity, as usual, second derivative. All right. Simplify again as much as you can. You get something that looks like this. When is it equal to 0? The first you need to realize is this will never be equal to 0. So it will never be equal to 0. So the next thing, it doesn't mean that there's no critical value because it cannot be equal to 0. You ask yourself, when is it undefined? You see, that's where you get other critical values now. It's undefined when the bottom piece equals to 0. So you see I have x equals to 0. And if I equate that to 0, I get x equals to 6. You see, all right. Although it cannot be equal to 0, it can be undefined. That's how I got two critical values. And when you test, you get positive there, you get positive there, and here you get negative. You know, positive, sorry, is the other way. So here it's a negative actually. So concave down is a negative and concave up is positive. So you get this kind of sign. And there you go, you have concave down, you have concave down, you have concave up. All right. All right. Now, when is it concave up? You say from 6 to infinity. When is it concave down? You say from minus infinity to 0 and from 0 to 6. Now, some of you be tempted to measure interval. You say it's concave down from 0 all the way to 6, all right? Please avoid doing that. The reason why I don't want you to say minus infinity all the way to 6 is because there is a problem at 0, all right? If you say that it's concave down from minus infinity of the 6, you're saying that there is nothing wrong at x equals to 0. Clearly, you can see the function that I gave you, the second derivative, there is a problem at when x is 0, all right? So in this case, you're going to say from minus infinity to 0, union from 0 to 6. So split into 2 to show that at 0, there is a problem, all right? Because the second derivative is undefined. Now, inflection point, notice it at 0, there's no inflection point, right? Because you have concave down on the left, and then you have concave down again on the right. So there's no inflection point. There should be a change in concavity for you to have an inflection point. Let's look at what happened at 6. There is an inflection point, right? Because it's concave down on the left, and then on the right, it's concave up. There's a change of concavity. But now there's one more thing that we need to test. You need to be able to compute f of 6. Remember that extra condition that I said? That number needs to, so the function needs to be continuous on that number, and there should be a change in concavity before you consider the inflection point. So we've seen the change in concavity, but is the function continuous at 6? The answer is yes, because when we started solving this question, I told you the function, the domain is a set of real numbers. It means every number you plug is going to work. So f of 6 equals to 0 is just an inflection point. All right. Now be careful in this example we've done, most of the time your inflection, like the inflection point that we've done, they usually part of the domain. They can be examples where you get an inflection point or you get some value here where there's a change of concavity, but it's not part of your domain. Then you need to tell me that 6, for example, is not an element of the domain, therefore no inflection point, all right? So you must always test to see that your function is actually continuous at that number before you can consider it an inflection point, all right? So practice and understand, because if you don't understand, then I'll give you a simple question, a test, you're going to struggle. And do these extra examples. So I ask you to find interval of increasing, decreasing, local max, local mean, concavity, inflection point. If you can do this accurately, then you should be well prepared for this section. And then look, there's another sketch there. It looks like the one that we did earlier. So see if you can also sketch this. All right. And that is it, guys. Is there any question from your side?